Hello, this is a mini project presentation on Parkinson's disease detection using machine learning techniques by Kiran Kumar, Sri Sai Teja, and Raghavendra Reddy. So coming to the abstract, so in various data repositories, there are large medical data sets available that are used for identifying the diseases. So Parkinson's is considered one of the deadliest and progressive nervous system diseases that affect the movement. It is also, it is the second most common neurological disorder that causes disability, reduces the lifespan, and still has no cure. To increase the lifespan of the elderly people, the machine learning algorithms are used to detect diseases in the early stages. Speech features are the main concept while taking into the consideration of the term Parkinson's. In this paper, the author is using various machine learning techniques like KNN, SVM, and logistic regression how these algorithms are used to predict the Parkinson's based on the input taken from the user, and input for the algorithms is the input for these algorithms will be the dataset. So based on these features, author predicts the algorithm that gives more accuracy. So the main aim of this is to develop a KNN and naive-Bayes model that can effectively classify Parkinson's disease based on the chosen data and the features. So this model can potentially aid in early diagnosis, improved objectivity, and clinical decision support. The scope of this project is like the scope of using this KNN and naive-Bayes for Parkinson's disease detection involves several steps like data acquisition, where we will be collecting the data from data that is relevant to the Parkinson's diseases such as voice recordings, brain scans from MRI, and also like movement patterns. And the next one will be the feature extraction, extracting relevant features from the data that can differentiate between healthy individuals and those with the Parkinson's disease. So, and the next step would be model training and optimization. The the KNN and naive-Bayes model is trained using a labeled dataset. This dataset consists of data points where individuals are already diagnosed with Parkinson's disease, that is positive or negative. The success of KNN and naive-Bayes model hinges on the quality and relevance of the data that is used. The existing system is that prior to the emergence of KNN and naive-Bayes models, Parkinson's disease detection relied on a combination of clinical assessment tools and imaging techniques. Here, below is the breakdown of these existing systems: subjectivity of clinical assessment, limited ability for early detection, and cost, and the last one is the cost and accessibility. The proposed system is that a proposed system for Parkinson's disease detection utilizes a machine learning algorithm called KNN and naive-Bayes for analysis. This is a simplified overview. Real-world implications might involve additional steps like data pre-processing, hyperparameter tuning for KNN and naive-Bayes model, and also exploring the different feature sets. Some research suggests combining KNN and naive-Bayes with other machine learning techniques or deep learning approaches for potentially, they will be giving even better performance. Coming to the design phase. So in this use case diagram, first the user will be giving the input as the spiral drawing and speech features, and then it goes into the next step, that is to predict the Parkinson's disease, and finally it comes up with the prediction results. This is the use case diagram. Coming to the class diagram, there will be user who will be giving the input as the spiral drawing and speech features. This will be taken into the web application. In the web applications, there will be drawing interface, process input, and show results tab. So the drawing will be going into the drawing tab for going into the pre-processing and getting the drawing data. In the similar way, the speech goes to the pre-process and get the speech data. These two will be going into the machine learning model, which will be CNN drawing, which will be trained by CNN drawing model and KNN model, and then then at the end the prediction result will be displayed. Coming to the architecture, so this is the PD speech data that will go into the pre-processing K-fold, and then it goes to the test data. This goes to the testing, and there will be trained data. This will be for the training of the model. Here the model will be getting trained, and there will be hyperparameters that we will be getting from the grid search, and then we'll be going into the testing. After testing, the model evaluates the input data and gives the performance metrics. Coming to the performance measurement function for multi-class classification, there will be unique class labels. The function starts by obtaining unique class labels present in both actual, y actual, and predicted y as y predicted arrays. So coming to initialization, this lists for true positives, false positives, true negatives, and false negatives are initialized with zeros for each unique class label. The next step is counting. It then iterates through each prediction and updates the respective count based on whether the prediction matches the actual label or not. And finally, it returns the values, like it returns the unique class labels along with corresponding TP, FP, TN, and FP counts for each class. Feature selection and K nearest neighbors classification. Performance feature selection using select K best with F classif scoring function to select the top 5 features. Then it splits the data into training and testing sets, applies KNN classification with different numbers of neighbors, and computes the error rate for each of the thing. And coming to the KNN model evaluation and performance metrics, this segment plots the error rate versus the number of neighbors, that is K, to find the optimal K value with the minimum error. Then it applies KNN classification with K is equal to 10 on the test set and calculates various performance metrics such as accuracy, precision, recall, F1 score, area under the ROC curve, that is AUC, negative predictive value, that is NPV, and specificity. This is the naive Bayes algorithm. So this part trains the Gaussian naive Bayes classifier on the training data and evaluates its accuracy on the test data. It prints the test accuracy of the naive Bayes algorithm. Performance metrics for naive Bayes algorithm. The code calculates various performance metrics for the naive Bayes model, appending these metrics to their respective lists. It first determines true positives, false positives, true negatives, and false negatives using the pref measure function. Then computes metrics such as AUC, accuracy, precision, recall, F1 score, NPV, and specificity, likelihood ratios, LR plus and LR minus, and odds scores are calculated based on these metrics with appropriate handling of division by 0 cases. Finally, it prints a detailed classification report for the model performance on the test set. So confusion matrix calculation. This block of code visualizes the confusion matrix of a naive Bayes algorithm's predictions using a heat map. Naive Bayes model evaluation. So this segment evaluates the performance of the naive Bayes classifier and computes various metrics for analysis. So the output would be Parkinson's disease prediction analysis. These will be the outputs. This will be the output for the Parkinson's disease prediction analysis. The patient having Parkinson's disease. Parkinson's. So this will be the outputs. Yeah, that's. Thank you.